Hello everyone, my name is Roghayeh Zamani. Welcome to my presentation entitled Deformation Assessment using Multi-look Multi-baseline SAR Interferometry. So at first I will start with some words about background of my study. Conventional InSAR technique compares two SAR images acquired from very same acquisition geometry in which the information of elevation or deformation can be captured separately through processing of the phase variations. And because the wavelengths of SAR sensors are about a few centimeters, so it's very sensitive to even very small displacements. And the basic idea is that we have two acquisitions and we can detect and compare different range measurements at different times, and by utilizing phase variations we can estimate the parameters. Apart from undeniable efficiency of InSAR, some main issues such as presence of artifacts and phase noise effects may impair interferometric phase quality and show some deficiency to cope with distributed scatterers. So to improve the efficiency, we use multi-loop multi-baseline InSAR technique. By utilizing multiple acquisitions in order to measure and monitor the displacements of the Earth's surface over the time, it can utilize amplitude and phase of the received data, and by the availability of multiple interferograms obtained from multi-temporal satellite observations, try to improve the accuracy of estimated parameters. And the parameters estimated through the data covariance matrix and multi-looking operation. In the SAR data, the observation vector for each pixel can be formed by collecting the observation complex valued as vector U, and this distribution is parameterized by the M by M complex covariance matrix for each pixel, where M is the number of images and E denoting the expectation. So the first step is a proper estimation of covariance matrix, and because the basic idea of covariance matrix is finding the similar pixels to the candidate cell and compute the averaging with purpose of noise reduction, so the method that we use for finding similar pixels play an important role. In this implementation, I use boxcar as a local and NLSR as one of the efficient non-local methods. The boxcar, a fixed size window, is centralized around each pixel, and the averaging in this method do not consider the statistical homogeneity of neighboring pixels. So in non-homogeneous area and low coherence regions, it may lead the results to lower accuracy and lose the image resolution. To tackle these problems, we use efficient non-local method called NLSR, and in this method the procedure is centered around the idea of checking the pixels to find the same statistical distribution as the investigated pixel. And then the covariance matrix can be estimated using a sum of weighted covariance matrices. The main peculiarity that made the NLSR approach extremely popular is its ability of filtering noise while preserving structures and discontinuities. In this framework, the parameters estimated in the maximum likelihood scene in order to perform 4D analysis of a study area. Following some statistical concepts of maximum likelihood, this model can be obtained. And that by minimizing the cost functions try to estimate the unknown parameters for each pixel. The minimization problem can be solved using numerical optimization through the joint estimation of Z and V, residual height and velocity. In this slide, we can see some experimental results obtained by using a stack of 15 Sentinel-1A images in C-band over northwest of Tehran, Iran, and the processing is limited to just permanent scatterers. Here we have estimated residual height and the estimated mean velocity of deformation, and both the presented maps in this slide obtained from NLSR estimation of covariance matrix. And the candidate pixels inside the yellow box in the zoom area are around the GPS station, for the evaluation of the mean deformation velocity, weighted parametric least square adjustment applied to GPS time series measurements from 2017 up to 2019, which determine mean line of sight velocity of minus 3.6 cm per year for the station. And the green line is the linear trend of deformation using GPS observations. In addition, a posterior variance factor test has been performed, which validated the least square adjustment. For the sake of comparison of maximum likelihood mean deformation velocity relevant to GPS station, we consider a 3 by 3 pixels window for GPS station, and we compute the average of velocities relevant to permanent scatterers in the window. And from the table, it is obvious that NLSR approach with far less differences between averaging results from the outcomes of GPS provides more accurate results, and we can see less sensitivity and variations in the results relevant to NLSR method by using different window sizes, which makes NLSR method very authoritative. Since discovering optimal window size and number of looks is a major issue in local methods that may affect the estimation of covariance matrix and displacement results. Moreover, boxcar method can ruin image structures and confuse the target contributions, especially in non-homogeneous regions. However, NLSR method has shown high filtering efficiency and great detail preservation capability at the same time. So in summary, the outcomes from GPS measurements for the experiments implemented in this study verified that using NLSR approach compared with boxcar has been improved the results close to 3 meters in height estimation and close to 1 or 2 centimeters in deformation velocity mapping, and with less value of a standard deviation in comparison with the amount dedicated to boxcar indicates less sensitivity to detect optimal window size. On the right side, we have a summary of implementation algorithm. Thank you very much for your attention.